Today I'll talk about how does ice flow and crack. And first, I just want to give a brief introduction. Actually, can you see the video right now? So this is Antarctica. It is a giant piece of ice sitting on top of bedrock. And glaciers are ice that viscous gravity current that flows viscously downslope into the ocean. And this continuous flow from ice sent from the continent into the ocean contribute to the sea level rise. And so this is a current prediction of the sea level rise in the next 300 years from a recent IPCC report. And ice flows as a fluid and is driven by gravity. As Ian was talking about just now, ice sheet and flows as a is driven by gravitational spreading. And ice sheet and ice shelves are two different regions. So ice sheet spread over the bedrock, ice shelves spread over the ocean. And note that this cartoon is exaggerated in a vertical scale. The actual aspect ratio between thickness and the length is about 1/1,000. So today I'll talk about two different stories, one about ice shelf, one about ice sheet. And the first story is about fractures that forms on ice shelves. And this is a interdisciplinary collaboration between both climate scientists and computer scientists. So again, this is a cross-sectional view of ice shelf along the flow. And here we focus just on the thin layer of ice shelves that float above the ocean. And I call it a thin layer because the thickness to length ratio is about 1/1,000, and it's really roughly on the same order of magnitude as a thin sheet of toilet paper. And currently, flow simulations do a decent job explaining the horizontal acceleration of velocities due to gravitational spreading. However, ice not only flows, it also breaks under the background extensional stress. And here is a beautiful example of the patterns of fractures observed from the surface. And because fractures occurs so much faster compared to the background viscous flow, it is currently difficult to resolve this fast fracturing process in a slow viscous flow simulation. And as climate warms, the ice surface can melt, and the meltwater can fill the fractures. And because water is heavier than ice, it can enhance vertical fracture propagation by hydrofracturing. And when the hydrofracture becomes unstable, it can break through the entire ice thicks and cause the retreat of the ice shelf front. So to give you some intuition, here is a analog experiment that you can easily do in the kitchen. And this qualitatively show that heavier fluids can cut through a brittle block of solid. And in this case, I was using gelatin. So strikingly, in 2002, almost the entire Larsen B's ice shelf collapsed within just a few weeks. And this rapid disintegration of ice shelf areas is widely believed to be caused by the hydrofracturing process I just described. And importantly, this loss of ice shelves can accelerate the upstream ice flow into the ocean, which could in turn impact sea level rise. So what are the physical conditions that's required for fracturing? And here, this is a fracture on a floating layer of ice. The ice flow accelerated towards the ocean caused this extensional stress that act to open the fracture. However, the weight of the ice itself act to close the crack. And if the crack is filled with water, the water is heavier and therefore impose additional hydrostatic pressure that can act to open the crack. So this system has been analyzed by Van der Veen using linear elastic fracture mechanics. And here we will use the same linear elastic fracture mechanics approach to identify 3 different outcomes for the fracture. So there is either no fractures, or we can predict crack with a stable depth. And the crack can also be unstable, meaning that it can just keep growing until it breaks the entire ice thickness. So what do we mean by stable and unstable cracks? We can quantify the crack stability by calculating the stress intensity factor as a function of the depth of the crack. And here, stress intensity factor is related to how fast the elastic strain energy release as the crack propagate. And this black curve is the stress intensity factor calculated from the contribution of both the extensional stress and the overburden stresses of ice. And the crack only grows if the black line is above the red line, which is the fracture toughness, and it is related to the energy required to break the ice. So for smaller crack, the extensional open stress dominant, which destabilizes the crack, so the crack can keep growing until the effect of the overburden stresses comes in, and that helps stabilize the crack. So this would be the final depth of the fracture. However, if we add enough water into the crack, we will only have one unstable solution. So in that case, the initial flaw will just keep propagating until it breaks the entire ice thickness. And next, it is useful to non-dimensionalize our equations to obtain 2 different dimensionless numbers. The first is the dimensionless stress, and that's the opening stress rescaled by the closing overburden stress of ice. The second dimensionless number is the dimensionless toughness, and that's the fracture toughness rescaled by the density times the gravitational acceleration times the thickness to the power of 3/2. So here we plot the crack stability as a function of the dimensionless stress and dimensionless toughness. Here, different graphs represent different amount of water in the cracks. And we can see that a dry cracks will be destabilized when it is fully filled with water. And now we will just focus on the simplest case when the crack is dry without the presence of water. So depending on the value of these two-dimensionless parameters, we have 3 different outcomes of the fractures. There can be no fractures. The fracture can have a stable depth. It can also be unstable. And next, we want to compare this with observations. Unfortunately, Earth is like a natural laboratory, and we have the data of velocity and thickness of ice shelf everywhere on Antarctica. And also fracture toughness can be measured in laboratory experiment. So here we can evaluate these 2 dimensionless parameters everywhere on ice shelves and put it back on this stability diagram. But we also need to know where fractures form. So here I train a deep convolutional neural network to detect the fracture patterns on satellite imagery. For example, on the left, this is a top view satellite imagery, and you can see these are the fracture patterns. And on the right is the prediction of the neural network. So here the grayscale is the likelihood that a pixel contains a fracture, and the white color here indicate the fracture location. And next, we can apply this neural network to detect fracture locations across the entire continent. So here, roughly 2 million pixels out of a total of 80 million pixels of the ice shelf areas are identified as fractures, and it's marked in white color here. And here is another close view example. The fracture patterns is marked in white color. So now we can use this fracture location map as a observational benchmark to compare with our model. And we recall the crack stability prediction. Here, the gray triangle is the parameter region we expect to see fractures. And now we plot the observational result. So here there are roughly 2 million points, and each point represents the parameters calculated from the strain rate, the thickness, the toughness at the fracture locations. And we find that the majority of this point where the neural network detect fractures lies in this gray area and are consistent with the physical regions we predict without any fitting parameters. And in addition, the scaling arguments give us a power law for this non-fracture to stable fracture transition boundary, and that agrees with the numerical solution from linear elastic fracture mechanics. So the benefit of this simpler scaling law is that it can be directly used in a large-scale ice sheet simulation without expensive computation. And this approach allows us to compare a model with observations over the entire continent, and that would be otherwise challenging without the machine learning technique. So, so far we only look at dry fractures without any water. A natural next question is what will happen if we add water into the cracks? And we have previously shown that crack stability switches from stable to unstable when we add water into the cracks. And here we upscale our analysis to the entire Antarctica, show that the majority of the ice shelves, which are marked in white color here, are under physical conditions that's vulnerable to unstable hydrofracture. And again, unstable hydrofracture is widely believed to be the cause of the collapse of the Larsen B ice shelves. Our result here indicate that warming climate can potentially threaten the majority of the ice shelves due to the transition from stable to unstable hydrofracture. So that's the first story, and so far I was just focusing on processes on ice shelves. For the next story, I'll talk about ice sheet blisters. And I want to start with saying that this project is really a group effort. The problem is inspired by field observations obtained by my colleague, Laura Stevens, and experiments and models are developed in collaboration with Howard and Danielle, who is also here at the workshop. Here is a beautiful image of a lake melted at the surface of Greenland. And you can see the surface is heavily fractured. And there are thousands of lakes like that on the surface of Greenland ice sheet. And in fact, you can find them easily on Google Earth. So these lakes do not always stay on the surface. And here is an observation of a lake that drains through a surface fracture and is almost entirely emptied. And the same observation of lake drainage can be found in different years and occurs around the same times of the year in June or July. So when lake water drains through a surface fracture and reach the bottom of the ice sheet, it deforms the ice sheet and causes vertical uplift. And we call this a water-filled blister. So here is the surface vertical motion measured by my collaborator, Laura Stevens. She used a dense network of GPS adaptive data to estimate the distribution of the blister height after the injection of water. And red color denote vertical, the positive vertical uplift, and blue is the negative uplift. So as you can see, after the injection, the blister height first increases, but then decrease in a timescale of a few days. And this decay of blister height is related to water leaking from the blister into the surrounding pore space along the ice bed interface. So for the rest of the talk, I'll focus on understanding this relaxation behavior of the height of the blister. So here we look at 3 different lakes for 5 different lake drainage events. And here are the data of the blister height that first peaks and then relax as a function of time. And here the relaxation time scale ranges from 12 hours to as long as 10 days. So Ian gave a beautiful talk about the evolution of the water flows beneath the ice sheet. And here I'll just treat this water flow as a porous media flow. And Darcy's law has been used for several types of drainage morphologies, such as films, linked cavities, and canals. The drainage efficiency of water flows beneath the ice can be described by hydraulic transmissivity, which is the permeability K times the thickness of the water sheet, H naught. And here's a classical Tsai and Rice model of lake drainage. So during water injection, the blister height increases, but during the relaxation, the height of the blister decreases when this fixed volume blister spread over the ice sheet interface. However, observations and theories suggest the existence of water network beneath the ice bed interface. So here we consider the effect of water leaking from the blister into the pre-existing porous water sheet. And here is a conceptual model. So here, this is a fluid-filled blister beneath a elastic medium, and the red arrows denote the flow directions. Around the blister, there are elastic stresses caused by the vertical deformation. And here, the elastic stress is proportional to the strain, which is proportional to the thickness of the blister over the radius of the blister. And along the fluid flow, we assume the Reynolds number is very small and the flow is laminar. So we can estimate the pressure gradient using lubrication approximation. And here we assume that the blister radius stays roughly constant. And we will show that later with a laboratory experiment. So the model is detailed in the supplementary material in our paper. And here I'll just quickly show the prediction of the blister volume that decays as a function of time in dimensionless unit. In particular, in the limit of low permeability, the relaxation approaches a exponential decay. And this is because when the permeability is small, the viscous resistance in the porous layer is much more important compared to the viscous resistance within the blister. So the relaxation dynamics is essentially governed by the balance between the elastic stress and the viscous resistance in the porous layer. The elastic stress are proportional to the volume of the blister, and the viscous stress are in the porous layer is proportional to the fluid flux, which is linked to the rate of change of the blister volume. So the simple balance between the two can yield a exponential decay of the blister volume. And here, the time is rescaled by a relaxation timescale. So we can obtain this relaxation timescale by scaling argument. By balancing the elastic stress with viscous pressure in the porous layer and consider the volume conservation, we can find that the relaxation times is inversely proportional to the sheet permeability and the sheet thickness, and also depend on the radius of the blister. So to check whether the relaxation timescale makes sense, we really need to test the model with a controllable system. And here I show a lab experiment performed by Danielle Chase. And Danielle is a PhD student here at Princeton working with Howard. And she found the system has a rich number of regimes that are reported in her paper published this year. But today I'll just talk about one particular regime that is relevant to ice sheet blister. So in Danielle's experiment, a thick elastic PDMS layer is adhered to a porous substrate with a non-permeability. And the viscous fluid, dyed in blue color, is injected and peels the interface between the elastic sheet and a porous substrate to form a blister. And in our experiment, after the fluid injection, we observed that the radius of the blister stays roughly constant, and the fluid in the blister can permeate through the porous substrate. So this is the measurement of the blister thickness profile obtained by Danielle. And again, we see that the blister radius is roughly constant. The benefit of experiment is that we can control the permeability of the porous substrate. And here I plot the measurement of blister volume that decay as a function of time for 3 different permeabilities. So we found that exponential solution agrees well with the experiment with just 1 finite parameters. And after rescaling the data with the characteristic time and characteristic volume, the data for 3 different permeabilities collapse onto our universal curves. And that demonstrates the success of our scaling in capturing the relationship between the relaxation time and the permeability. So next, I'll upscale this model to understand the field observations. And first, we see that our exponential solution, which is shown by the black dashed line, it fits well to the blister height relaxation data. And second, we see that the wide range of relaxation time can be explained by different estimate of transmissivity of the ice bed interface. And what this shows is that ice sheet relax faster on the ice bed interface with higher transmissivity. And next, we will put all these data set on the same plot. Again, this is blister height that relaxes over time. And after rescaling the height with initial height and the time with a relaxation time scale, we show that the curves collapse onto a universal shape and can be described by our model. So the collapse of the data onto a single curve indicate the universality of this uplift relaxation process controlled by the interaction between elastic deformation and viscous resistance in the porous flow. And finally, to say the value of this work to field scientists is that we can actually use this relaxation curve to estimate the transmissivity of the porous water sheet, which is typical kilometers beneath ice sheet and very difficult to measure in the field. And I guess for the interest of time, I'll skip this slide, but this is just, we use this method to estimate the transmissivities of the water flow beneath the ice sheet.
You have 6 minutes.
Oh,
you're good.
Okay.
I think.
Good. All right. Yeah. Okay. Good. Thank you. And yeah, I guess well, I have a few open questions, so it'll be good to discuss those. And I guess I only summarize by saying that I find the interactions between fluid flows, elasticity, and porous flows fascinating, and they can be found everywhere in the cryosphere. And here I show 2 examples. First about ice shelf hydrofracture, where we combine observations with fracture mechanics to develop a crack stability diagram and show that most Antarctic fractures are under the conditions that are prone to destabilization when it's fully filled with water. And the second story about ice sheet blister, we use a lab experiment to understand ice sheet blister relaxation that's observed in the field. And we also can use this lake drainage event as a natural probe for transmissivity, which is typically challenging to measure in the field. And I guess for the next 5 minutes, I thought I would just use this opportunity to pose 2 unsolved questions that I think will really benefit from the expertise from this audience. The first open question is related to mechanical instabilities. So here is the top view of Thwaites Glacier, and ice flows from the upper right to the lower left. You can see this spectacular regular wrinkle patterns, and these regular patterns can actually be found on almost all ice shelves, and this wavelength pattern, the wavelength is about the same order of magnitude as the thickness. Importantly, this wrinkle spacing to some extent determine the size of the icebergs. So we can see the ice shelves with these patterns in 1996 has broken into icebergs in 2014. And here is a cross-sectional view along the flow. You can see the surface and bottom topography of ice shelf. Again, here the vertical axis is exaggerated In this bottom plot, where we use the same horizontal and vertical scale, you can see the actual wavelengths of these features is about 3 to 4 times the thickness of ice. And we know that periodic wrinkle can form when we compress a floating sheet of elastic sheet. But ice shelves are actually undergoing extension rather than compression. So what drives this observed periodicity is still not well established. And the second open question is relevant to the granular mechanics of sea ice. This again echoes John's point that we don't really know the constitutive law of sea ice. So different from ice shelves, sea ice formed from the freezing of ocean surface, and its thickness is observed to be about 1 order of magnitude smaller than the thickness of ice shelves. So sea ice tend to break into pieces that are called ice flows, and Dominic and John has 2 beautiful papers on the interactions between these ice flows. So on this, here we can see individual ice flows in this high resolution satellite imagery over Antarctica, where the dark color represents ocean and the white is the ice. Here is another example farther away from the ice shelves. And you can see in the left image, the ice flows are almost jammed together, but in the right image, the pieces are smaller and less jammed. And if we zoom out, you can see the large scale pattern, special pattern of this sea ice distribution. And this lower right image is really just a tiny part of this upper image. So as John pointed out, the rheology of sea ice used in climate model is highly uncertain. And in particular, how to describe the bulk motion of this 2-dimensional granular material, which contains pieces that can collide and breaks, is still not well established. And I just want to finish by saying that now we actually have newer and higher temporal spatial resolution of satellite imagery. And Suji mentioned in his talk that for his experiment, being able to see things makes a big difference. So I think it's exactly the same story here. Now is an exciting time to revisit some of the unsolved questions because now we can see things better.